Imagine a universe hidden from our everyday sight, a realm where the familiar rules of physics bend and twist. This is the quantum world. It's all around us. It's within us. It governs the very fabric of reality. For decades, we've peered into this strange place. We've marveled at its bizarre behavior. Now, we are on the cusp of harnessing its power. We are learning to build machines that think in the language of the quantum. This is the dawn of quantum computing. This journey is not just about faster computers, it's about a fundamental shift in how we understand the universe. It's about unlocking new ways to solve problems that are currently far beyond our reach. Think of the biggest challenges facing humanity. Quantum computing offers a new key. To understand quantum computers, let's first look at what we know. Classical computers, the ones in your phone or on your desk. They are magnificent machines. Truly, they have transformed our world in countless ways. They think in a very simple language, the language of bits. A bit can be a 0, or it can be a 1, like a light switch. It's either off or it's on. There's no in between, not for a classical bit. These bits, these zeros and ones, are the foundation. All the amazing things your computer does, from streaming videos to sending emails, it's all built on long strings of these simple states. Calculations are done by flipping these switches, one by one, very, very quickly. But there's a limit. Let's delve deeper into this idea of superposition. It's one of the cornerstones of quantum mechanics, and it's what gives qubits their remarkable abilities. As we said, a classical bit is definite, 0 or 1, but a qubit, before we measure it, exists in a cloud of probabilities. It holds the potential to be 0 and the potential to be 1. Simultaneously. It's a mind-bending concept, but it's how the universe works at its most fundamental level. Imagine a dimmer switch for a light. It's not just on or off, it can be partially on at many levels of brightness. This both-at-once characteristic is incredibly powerful. If you have just one qubit, it can represent two states, 0 and 1, at the same time. Now, what if you have two qubits? It gets even more interesting. There's another quantum phenomenon just as strange as superposition, perhaps even stranger. It's called entanglement. Albert Einstein famously called it spooky action at a distance, and it's a perfect description. Imagine you have two qubits, and you entangle them. This means their fates become intertwined. They are no longer independent entities. They form a single quantum system, even if they are miles apart, or light years. What happens to one entangled particle instantly affects the other, regardless of the distance separating them. If you measure the state of one qubit, say it collapses to a 0. Section 5. Unlocking nature's secrets. Quantum in medicine and materials. So, we have these strange quantum properties, superposition and entanglement. What can we actually do with them? The potential applications are vast. Let's start with medicine and materials science. Nature itself is quantum mechanical. Molecules, atoms, the way drugs interact with our bodies, these are all governed by quantum rules. Classical computers struggle to simulate these systems accurately. They can only approximate. Quantum computers, on the other hand, speak nature's language. They could simulate molecules with incredible precision. Imagine designing new drugs, not through trial and error in a lab, but by simulating how different molecules will behave inside a quantum computer. This could rapidly accelerate the discovery of new medicines. For diseases like cancer, Alzheimer's, or even new viruses, personalized medicine could become a reality. Drugs tailored to your specific genetic makeup. The same power applies to materials science. Want to create a new type of battery? Section 6. Tackling giants, climate change and complex problems. Beyond medicine and materials, quantum computers promise breakthroughs in tackling some of the world's most complex challenges. Consider climate change. Understanding our climate is incredibly difficult. It involves countless variables: ocean currents, atmospheric chemistry, ice melt, solar radiation, all interacting in intricate ways. Our current climate models are good, but they are limited by classical computing power. They have to make simplifications. Quantum computers could revolutionize climate modeling. They could handle far more complex simulations with many more variables and interactions. This could lead to much more accurate predictions, helping us understand the impacts of climate change better, and crucially, helping us find more effective solutions. Perhaps by optimizing renewable energy grids, or by discovering new ways to capture carbon dioxide. The scale of the problem requires a new scale of computation. Section 7. A milestone achieved. Google's quantum supremacy moment. The journey towards powerful quantum computers is long, but there have been significant milestones along the way. One such moment captured headlines in 2019. Google announced it had achieved quantum supremacy. This was a landmark claim. They used a quantum processor named Sycamore. It had 53 functioning qubits, a relatively small number but still significant. Google said Sycamore performed a specific calculation in just 200 seconds. What was so special about this calculation? Google claimed that the same task would take the world's most powerful classical supercomputer something like 10,000 years to complete. This was the basis for the quantum supremacy claim. It meant, for this one specific, carefully chosen problem, a quantum computer had outperformed any classical computer. It was a demonstration of potential, a proof of concept that quantum speedups are real, not just theoretical possibilities. Now, the term quantum supremacy is a bit contentious. Some researchers prefer quantum advantage. Section 8. The Path Forward. Challenges on the Quantum Frontier. While the promise of quantum computing is dazzling, the road to building large-scale, fault-tolerant quantum computers is paved with formidable challenges. We are still in the very early days. Think of classical computers in the 1940s or 1950s. They were huge, expensive, and unreliable. Quantum computers today are in a similar stage. They are experimental, delicate, and prone to errors. One of the biggest hurdles is decoherence. Qubits are incredibly sensitive. Decoherence happens when qubits interact with their environment. Even tiny vibrations or stray electromagnetic fields can disturb their fragile quantum states, causing their superposition and entanglement to break down. This leads to errors in calculations. Section 9. The universe in a qubit, our quantum future awaits. We stand at a fascinating threshold in human history. The quantum realm, once a domain of pure scientific curiosity, is now becoming a playground for technological innovation. Quantum computers are not just another upgrade, they represent a fundamental shift in our ability to process information and understand the universe. The journey is complex, filled with challenges, but the potential rewards are truly transformative. Imagine the discoveries that lie ahead, the problems we might solve. From revolutionizing medicine and materials science to tackling climate change and unlocking the secrets of AI, quantum computing could reshape our world in ways we can only begin to imagine. It's a tool that could help us understand nature at its deepest, most fundamental level. Because nature itself is quantum. To simulate it, to truly grasp it, we need computers that speak its language. That language is the language of qubits. The breakthroughs we've seen, like Google's experiment, are just the early tremors of an approaching earthquake. There's still a long way to go. Many brilliant minds are working tirelessly to overcome the hurdles of decoherence, error correction, and scalability.